So to finish up section 3, we really just have a couple of little kind of loose ends to wrap up and a couple of little tidbits here to finish. There's one very specific example I want us to talk about, and that's if we're asked to do a limit of a piecewise defined function. And this is not so much understanding limit as it is understanding what a piecewise function is back from algebra class. And these could be one-sided limits, or they could be the traditional limits that we have to look at from both sides. And we're going to do this analytically. Everything in this section is analytical. So let's say our f of x is x squared minus 4 when x is less than or equal to 1. And then it's x plus 2 for x greater than 1. So this is a piecewise defined function because it's defined by two different functions on two different parts of its domain. For x values less than or equal to 1, it uses the x squared minus 4 graph. For x values greater than 1, it uses the x plus 2 graph. So it's made up of two different pieces. The only real problem we have when it comes to limits is what's happening at 1, because 1 is the place where we jump from one function to the other. X squared minus 4 is a parabola, and a parabola is a nice, smooth, continuous function. And we said earlier, when we're working with continuous functions, direct substitution is going to work just fine. X plus 2 is a linear function, which again is a nice, smooth, continuous function. So direct substitution is going to work just fine. The only issue we're going to come across is at x equals 1 when we switch from one function to the other. But just for an example, we're going to look at a bunch of different limits. So the limit as x approaches 0 for f of x. Now, we don't have to approach 0 from really far away. And back in the definition, in an earlier section, we said the limit is when we get arbitrarily close to 0. So there's really no set definition of how close or how far. It's just kind of in the neighborhood of 0. So there's not an exact definition of how close to 0 we need to be, but it really needs to be pretty close. So in the neighborhood of 0, we need to know what's going on with this function. And around x equals 0, now a limit doesn't always look at what's happening exactly at 0, but it's wondering what's going on with the y values near x equals 0. So with this piecewise function, when x is equal to 0, it's strictly using x squared minus 4 because it's using x squared minus 4 for every x value less than or equal to 1. And 0 is clearly in that interval. So we can do this with direct substitution by plugging 0 just into the first piece and getting negative 4. Or if we wanted to do the limit as x approaches 3 for this function. So we want to look and see what's happening on this function in the neighborhood of x equals 3. So in a little arbitrary neighborhood of x equals 3, this function is using the x plus 2 line. X equals 3 is clearly a value greater than 1. So we can approach 3 from the left and from the right by staying on the x plus 2 line. So we can just plug 3 into x plus 2 and get the answer with direct substitution. So as long as we're avoiding the x value of 1, we can do limits of piecewise functions with direct substitution. We just have to pick the correct piece. The problem comes in when we want to do the limit at that breakpoint. So I need to move my screen a little, but I'll scroll back up. Now if we say, well, what's the limit as x approaches 1 from the left for f of x? Now remember, left means smaller values. As we approach 1 from the smaller values, we don't actually have to equal 1. We just want to approach it from values that are smaller. So you can always think in your mind of some examples. Well, if I'm approaching from values that are smaller than 1, I'm approaching from values like -2, -1, 0. Those are all values smaller than 1. So which one of these pieces would use -2, -1, 0? Which one of these pieces uses values that are smaller than 1 or to the left of 1? It would be the first piece. So the first piece uses x values that are to the left of 1. So to figure out the left-hand limit, or the left-sided limit, we would plug 1 into the first piece. So we would say 1 squared minus 4, which is -3. And then to do the right limit, we want to approach 1 from the right. To the right of 1 are values larger than 1, values greater than 1. So values greater than 1 are like 2, 3, 4, and 5. So we want to know when x is allowed to take on the values 2, 3, 4, and 5. And it says right here, when x is greater than 1. So when x is greater than 1, this function is using x plus 2. So we would plug the 1 into our x plus 2 expression, and we would get 3. So from the left, when x is 1, from the left it looks like it's approaching -3, but from the right it looks like it's approaching +3. So remember, like we said in section 2, what that means for just the standard limit for the function. When the left and the right do not agree, that means there's a big old gap in our graph. We've got this big old jump, and that means, and actually technically we should not use an equals sign, this limit does not exist. In order to have an answer to a limit, the left and the right must meet in the middle at the same number. And our left and our right do not meet at the same number. From the left it's -3, from the right it's +3. Another piecewise defined function that looks a little bit different, if we said g of x is we are going to say it's x cubed plus 2x. As long as x is not 4. As long as x is not 4, it's x cubed plus 2x. If x is 4, it's going to be 3x minus 1. So when we define the domain here, we're not using less than, greater than. We're using is equals, is not equals, which is a little bit different. So this is only throwing out one single value. When you're only throwing out one single value, that's going to create a hole in the graph. And we said in 2.2, holes are okay with limits. We can still do limits at holes. So if we wanted the limit as x approaches 0 for g of x, where does g of x take on an x value of 0? Well, it takes on, or it resembles the x cubed plus 2x graph everywhere but at 4. So that includes 0. So at 0, it would be taking on the x cubed plus 2x value. So we'd plug it into there. So 0 cubed plus 2 times 0 is 0. And what about the limit as x approaches, let's say, -2 for g of x? G of x is going to take on an x value of -2 using the x cubed plus 2x expression. It takes on that value at everywhere except for x equals 4. So we would do -2 cubed plus 2 times -2, which is -8 minus 4, so -12. Just like in the last problem, really the only place we run into trouble is at 4. That's the only place we need to be careful of. So we're going to look at the left and the right and then our traditional limit. The limit as x approaches 4 from the left. So with limits, we're not actually asking for the function value. We're saying, what does it look like the function is getting close to as x gets close to 4? Now, the way this function is defined is at x equals 4, you should use 3x minus 1. Everywhere else, you should use x cubed plus 2x. So if we're just getting close to 4, but we're not actually on 4, if we're just getting close to 4, then we're still on this graph. So as we approach 4, we're approaching it on the x cubed plus 2x graph. So we should plug 4 into the x cubed plus 2x graph to see what it looks like it's approaching. So this is 64 plus 8, which is 72. And really, that would be the same exact thing from the right-hand side. Because as we approach from the right, as long as we're not actually on x equals 4, we're following this function. So whether we're coming from the left or from the right, we're following x cubed plus 2x. So from the left and from the right, it looks like we're approaching 72. Now the actual function value at 4, g of 4, means tell me what the point is at 4. This is our actual function value. This is what happens when you plug 4 into the function. This is different than the limit. So if I actually want to plug 4 into that function, that is where this guy comes in. If I actually want to plug 4 in, I need to go to the second piece. So that is the 3x minus 1 graph, which is 12 minus 1, which is 11. So I did that to try to trick you, because now if we want just our general standard limit, the limit as x approaches 4 for g of x, that has nothing to do with the function value. What we said back at the beginning of 2.2 is the limit will exist, and it will be equal to whatever your left and your right approach, as long as they approach the same number. So our left and our right both approach 72, so the limit is going to be 72. This graph when we're only throwing one single number out, that just creates a hole in the graph. Now this graph is not going to be accurate. I just want to give you a quick little example of what this thing looks like. So we're following along one graph, and then they say, throw 4 out and put it somewhere else. And then once you do that, then you can keep following the same graph. This is an example of what this description of this domain means. So you can follow one single graph everywhere except at one particular spot. And at that particular spot, we jump away to a different value. And that's what we have here with our left and our right limits. It looks like they're approaching one number, but the functional value is somewhere else. So as we approach from the left and the right, it looks like we're approaching one value, but the functional value is actually somewhere else. Really, all we have here is a hole, and holes are not a problem with limits, because with limits, we don't actually want the functional value. We're just following the trend of the graph and saying, what does it look like the functional value is approaching based on the trend in the graph? So based on the trend in the graph, it looks like it's approaching 72. The example we did before was different because we actually cut that graph in half. So this graph, and again, this is not those exact functions, but one of these was like a half parabola. And then the other one was a straight line. And there's a big giant gap in between. And that's why we couldn't do the limit, because as we approach from the left, it looked like it was approaching one number. As we approach from the right, it looks like it's approaching a completely different number, a completely different y value. From the right, the y value is up here. From the left, the y value is down here, even though they both have the same x value. So that's why the limit on the first one did not exist, and the limit on the second one did. And it all has to do with that notation we see. The notation for the first one, and I'm sorry I'm going crazy with the scrolling, was less than greater than. That could create a gap if your left and your right don't match up. With the equals not equals, that just means we're just moving a single point and we're just creating a hole. And holes are not a problem with limits. Holes are perfectly fine. So there are two limits that give us an indeterminate form that I can't exactly explain to you how to fix yet, and we just really need to memorize them. And these are special trig limits. The first one is the limit as x approaches 0 for sine of u over u equals 1. The reason I used u is because there could be anything in that spot. And as long as what's inside of your sine function matches the denominator, the answer will be 1. So an example of this would be the limit as x approaches 0 for the sine of 2x over 2x. As long as the angle matches the denominator, the answer is 1. Or the limit as x approaches 0 for the sine of x cubed minus 5 over x cubed minus 5 equals 1. As long as the angle matches the denominator, the answer is 1. Now the tricky part comes in when they don't match. If you tried to plug in 0 and do direct substitution, you'd get 0 over 0. And for right now, there's no way to fix it. I don't have a good way to tell you how to fix it yet. I will as the semester goes on, but based on what we know right now, this is just a special trig limit that we have to know. So the trick with these is if they don't match, we have to learn how to get them to match. And it's actually really easy. The answer will be 1 if they match. So if we were asked to find the limit as x approaches 0 for sine of 4x over x. Now, from trigonometry, we should know that the 4x is an angle, and you cannot just pull the 4 out of the angle. And for our purposes here in calculus, we're never going to mess with that angle. We're going to leave the angle alone. What we want to try to do is get the denominator to match the angle. So the angle is set. The angle is always set. So if I want to be able to use this rule and say that the answer is going to be 1, I need to get the denominator to say 4x. So what I'm going to do is I'm going to put a 4 down there. And I'm allowed to do that as long as I do the opposite somewhere else. So technically I haven't really changed the problem because I've done opposite operations that would cancel each other out. So putting a 4 down there in the denominator is like dividing by 4. So the opposite of divide by 4 is multiply by 4. So technically those 4's that I just added in green would cancel each other out and not make any difference in this problem. But now I have this fraction that matches my rule. And the limit for that fraction is 1. And we can take this coefficient and we can pull it out. And we can say this is 4 times the limit as x approaches 0 of sine of 4x over 4x. That limit is 1, and we have our 4 in the front, so 4 times 1 is 4. So our goal is to get them to match by multiplying or dividing by some extra numbers to make them match. Don't ever change your angle. The angle is set. The only way you're ever allowed to change the angle in a trig expression is if you want to start applying some trig identities. And most people don't want to go there. So what we can do, which is much easier, are some quick little algebra or computation techniques. So we can multiply and divide by 4. That would be a lot easier to get them to match. So here we had the extra 4 in the angle. So what happens if our extra number is in the denominator? So if we want the limit as x approaches 0 for sine of x over 2x. So the angle is what dictates the direction this problem is going to go in. And the angle tells us how we need to get these guys to match, because we're never going to mess with that angle. We need our denominator to just say x if we want this limit to work. Right now, there's an extra 2 down there. Those two terms, actually they're not terms, they're factors. Those two factors in the denominator, they're not committed to each other. They're just kind of sitting there next to each other. We're allowed to separate them. We can really pull that 2 out to the front the same exact way we pulled the 4 out front in the last problem. You just need to be careful because the 2 is in the denominator. So if we pull it to the front, it's going to come to the front as a half because it's coming from the denominator. So this is really 1/2 times the limit as x approaches 0 of sine x over x. Now they match. My angle and my denominator match, so that limit is 1, and I have 1/2 times 1 equals 1/2. So as long as you can get your angle and your denominator to match, the limit's going to be 1. If there's extra numbers, if there's an extra number in your angle, you'll have to multiply and divide to get them to match. If there's an extra number in your denominator, all we have to do is pull it out as a coefficient. So that's one of our special one of our special trig limits that involves sine. There's another one that we really don't use as much that involves cosine, and this is the limit as x approaches 0 for 1 minus cosine u over u. And this one is equal to 0. So again, I used u because as long as the angle and the denominator match, they could really be anything as long as they match. This is a much better case to see why we don't ever want to mess with the angle, because our numerator there has 2 terms in it. So we definitely don't want to think about factoring anything out, because in 2 terms we would have to factor it out of both of them. And that first term is a 1. We really only want to mess with the denominator. So whatever that u ends up being, that's going to dictate the direction that this problem goes in. So we look at that angle. We look at that angle to help us decide what to do with the denominator. We try to get our denominator to match the angle so that we can use the rule. So one really quick example with cosine, even though sine is the much more common one that we see, this one's going to be a little bit harder. We've got the limit as x approaches 0 for 1 minus cosine of 3x over 2x. Now if you try to plug in 0, if you try direct substitution, you're going to get 0 over 0. That's why these are special trig limits, because if you try direct substitution, you're going to get indeterminate form, and we don't have an analytical way to fix it. So we just have to remember the answer, and remember that if I can get the angle in the denominator to match, then it's going to work. So right now, my angle is a 3x, and we are never going to mess with the angle. I need my denominator to be a 3. So how can we turn a 2 into a 3? It's not as simple as just multiplying or dividing by a whole number, but you can break it up into a couple of steps if you want to. If you have the completely wrong number there, what you can do is say, well, I need to get rid of the number I currently have and replace it with the number that I want. So dividing by 2 will get rid of the current number. Multiplying by 3 will replace it with the desired number. So if I multiply in the denominator by 3/2, that will change my denominator to 3. So multiplying in the denominator by 3/2, what did we do up here when we had that same situation? I can introduce a number in the denominator as long as I also introduce it out front. So in this first example with sine, we had to introduce a 4 in the denominator and a 4 in the front. So here, I can introduce a 3/2 in the denominator as long as I also introduce a 3/2 in front. Technically, they would cancel each other. But we're using that to get the angle in the denominator to match. So now this is 3/2, the limit as x approaches 0 of 1 minus cosine of 3x over 3x. Now they match, and that cosine limit is 0. And the reason we don't see this all that much is because no matter what we multiply or divide by to get this to work, because that limit is always 0, the answer is always going to end up 0. So it's not very interesting. It's not very fun to play around with because you never get a different answer. Really, you never get a different answer. It always ends up 0. The sine one is a lot more fun to play with because the limit is 1, so introducing different numbers will give you different answers. So those are a couple of special trig limits we might come across where direct substitution gives us an indeterminate form and we really don't have an analytical way to fix it yet. But if we can get the angle in the denominator to match, we do have a rule as to what that limit needs to be. And remember from section 2, analytically is not the only way to do a limit. In section 2, we also learned a graphical way to do a limit and a numerical way to do a limit. So we really could have looked at these two trig limits graphically and numerically and seen that the answers were going to be 1 and 0. All right, so the last two things in section 3, so we're going to wrap this up here. One of them is a really weird limit that does not exist. And I want to show you the graph, and I'm going to open Desmos, and hopefully this works nicely, but we will see. If you've never used Desmos before, it's very similar to your graphing calculator, except it's a lot more user-friendly. When it comes to like finding maxes and mins and intercepts, you can literally just point with your mouse at the spot on the graph that you want to identify. On your graphing calculator, it asks for like left bounds and right bounds and guesses, and you have to go through this whole process to find things. But on Desmos, it's everything's just point and click, so it's a lot nicer. So there's this one really crazy graph, and it's the sine of 1 over x. So let me see if I can graph this for us. Sine of 1 divided by x. Yes, wonderful. It is crazy. Look at that thing. We're going to talk about the limit as x approaches 0. So remember, the answer to a limit is the y value. What does it look like the y value is approaching as x approaches 0? That's a good question. I see a solid block of red. This graph starts to oscillate so quickly as x gets close to 0 that we can't even tell what is going on with the y. I know that it's definitely staying in between positive and negative 1, but it starts to jump up and down so fast, we can't pinpoint an exact y value. So this really crazy oscillating behavior is one very weird example of a limit that we cannot do. And it doesn't happen a whole lot, but it's something that every calculus book that I've ever seen, it always points out. And if you tried to do a numerical graph for it, you wouldn't really be able to see a pattern. It would all depend on the numbers that you picked. Your numbers in your table would kind of jump all over the place. So this one really weird limit the limit as x approaches 0 for the sine of 1 over x. So at the beginning of this section, I said you should always try to just do direct substitution. If we tried to plug 0 in there, you would be doing the sine of 1 over 0. Well, 1 over 0 is undefined, but technically, since it's a limit, 1 over 0, if you divide by a number that's approaching 0, which means it's getting smaller and smaller and smaller and smaller and smaller, 1 divided by something smaller and smaller and smaller is going to go to infinity. This is really the sign of infinity. Well, sine is an oscillating graph. Sine doesn't ever do one definite thing. Sine is always going back and forth between positive and negative 1. So as we get close to 0, it just does it faster and faster and faster. So the sine of 1 over x graph that we just saw in Desmos looked something like this, and this is, well, let me see if I can copy it good. Literally. This is positive 1. This is negative 1. We cannot pinpoint exactly what is happening at x equals 0. It is just going crazy here. It is going so crazy. If we keep zooming in, it's just a solid block. This is just a solid block of numbers, a solid block of graph, no matter how much you zoom in. Zooming in is not going to make it look any nicer. So this particular limit, when we see this crazy oscillation, it does not exist. Now, it only does not exist at 0. We can plug other x values in and get an answer just fine. I can figure out what's going on at x equals 1. I can figure out what's going on at x equals a half or at x equals negative 2. It's just at x equals 0 that this thing just goes psycho. All right, very last thing in this section is called the squeeze theorem. And this is helpful for when we don't know what function we're working with, or we really just have no idea how to do the limit. So this allows us to figure out the limit based on some other functions that are similar that we do know the limit for. So the squeeze theorem says, and if you have a book or you follow along with the book, it's on page 75. It says if we have three functions, f, g, and h, and we know that f of x is always less than or equal to g of x, which is always less than or equal to h of x. So these are the y values. I know the f's are always the smallest, the h's are always the biggest, the g's are always in between. This is for all x near a. So a is what we're trying to find our limit for, except possibly at a, because with limits, we're not so concerned with what's happening at that exact point. We're just looking what's happening near that point. If the limit as x approaches a for f of x is equal to the limit as x approaches a for h of x, so your front function and your back function have the same limit, then this guy that's stuck in the middle, since the y value is our limit, and these two, f and h, have the same answer, g has got to be the same as well. This is helpful when we don't really know anything about G except the fact that it's sandwiched in between two other nice functions. So G could be something really, really crazy that we don't know much about, but we do know that it's always sandwiched in between some really nice F function and some really nice H function. And the F and the H have a nice limit. So one thing that we use this for, we use it a lot in Calculus 2. So we just introduce it very briefly here, just the idea of a squeeze theorem, but we expand on it a lot more in Calculus 2. So the idea is if I know that I've got, let's say, my H function and my F function. My F function has the smaller values, my H function has the bigger values, and then I've got this G function that's doing really crazy stuff in between, but I know it always stays in between. If F and H have the same limit out here at A, then G has to also have the same limit out there at A. So that's the idea. If G is in between them, then G's got to have the same limit. If it doesn't have the same limit, then at some point G has to break out, kind of break out of their grasp.